strong damping for infinite dimensional open systems.
Thanks, Lanjana, and thanks for the invite to this nice workshop. Yeah, so this is a joint work with Simon, who is there in the audience. Hello, and Lanjana. And it's like some work we've did at the beginning of my PhD, and then there's like some a bit more recent result, and I walk you through all of that. And I start quite slowly, I think, with just kind of motivating what actually the Zeno effect is, and I start with the closed system because then the interpretation is a bit clearer. So, okay, closed system, what do I mean? We have just Schrödinger dynamics governing the system. So therefore, our dynamics is governed by a unitary group generated by the Hamiltonian. I can like pictorially visualize it like that. And then the simplest setup is we just do projective measurements. We start with some initial state, psi 0, and then we ask the question at each of these measurements, cool, am I still in like state psi 0, or did I move out of it? We have n frequent measurements, and the question is what happens if we crank up the measurement frequency n to infinity. And the quantum Zeno effect predicts that if we look at the probability that we find the initial state at all of these measurements, as n goes to infinity, that just approaches 1. So we kind of we have frozen the system in the state, in the initial state. It did not move out. That's also why we came up with the, or not we, but like people came up with the name ages ago, because there is like this Greek philosopher saying, okay, if there's an error in the air, and you look at it at each given moment in time, it's kind of stationary, so it should not move. Obviously, that's wrong, but quantumly, there's like some truth to it. Because it's like frozen in this initial state. Okay, you can like generalize this. You can look at initial state being mixed and general projective measurements for normal measurements. Same setup, you apply it like n times. Okay, and you can ask the question, what happens here? And you can ask the question, okay, what's the effective dynamic of the process? So does this operator product here, as n goes to infinity, converge in some reasonable sense to some effective dynamics? And what we formally expect, and what's also been proven in the Hilbert space, or like in the unitary group setup, that okay, for H bounded, but also H being unbounded and kind of nicely behaving with P, that this in some sense converges to an effective Zeno dynamics, which looks like that. So we just stay on the effective on the Zeno subspace, but we have like some dynamics which governed, which makes it like non-trivial on within that subspace. And okay, how do we get like kind of the Zeno effect from the measured probabilities back from the effective dynamics? Well, okay, that's kind of very easy. So the probability of measuring p n times is given by like this trace where the operator product appears. Okay, if we know that this converges, in that case, like in the weak sense, then we get like this effective Zeno dynamics back. And because the Zeno dynamics itself is unitary, it just cancels it out. And we obtain that this probability converges to the probability of finding P in the initial state at time 0. So again, we have like some kind of frozen measurement probability. And the dynamics didn't take us out of the Zeno subspace, let's say. So that's the closed picture. What I'm more interested is the open system setup. So we have some system in some environment, there's some interaction. We just look at like recoupling of a system and environment. And so as we've seen like many times in this workshop, we consider Markovian dynamics or Lindblad dynamics. So we have some generator or some Lindbladian L. And what we get out as kind of dynamics is some semigroup of quantum channels, which looks like that. And okay, in general, this thing will just be strongly continuous. So like continuous for fixed input state. But if L is a bounded generator, even okay, we know that this is a continuous and operator norm on the trace class. So this is the setup. Again, okay. We can slightly generalize now also what we consider as the actions in between. Why only projective measurements? We can look at like general applications of quantum channels, or even more general, just quantum operations. So we could be interested in generalized measurements where like each of the generalized measurement operators are just trace like completely positive, but trace non-increasing. So this would be covered. And then the Zeno setup is you apply, you have your dynamics, you let it go for some time t over n, you apply the quantum operation m, you evolve again for some time t over n, and you do this n times, and you're interested in, okay, what happens if measure application frequency n cranks up to infinity. Okay, so what's the effective dynamics, or does this operator product converge in some reasonable question? That's kind of like the question of this talk from now on. And there are some results on that, like that's a general Banach space result for contraction semigroups. If M is a projection again on this Banach space, then Matolsky and Schmidt-Coyle proved that, okay, we get again something which exactly looks like the thing I showed you earlier, some effective xenodynamics on the Zeno subspace. And this is for a bounded generator and an operator norm. And then Milbus and Wolf in 2019 extended this to like more general quantum operations where we have some spectral condition being satisfied. I will talk about the spectral condition in the following. And also they found like an effective xenodynamics also on some Zeno subspace. Now I need to actually say what this P is because it's not like immediately clear from the definition of M. P is just a projector invariant subspace of M, right? So I mean, in some sense, you can think of M being like the way stronger part here, and you have some mixing effect because like you apply M further and further, and so often, okay, you just converge into the fixed point space of this M. And the question is the Zeno question is whether this is stable if you have like an semigroup dynamics applied in between. That's the main question. So those are the previous results. What I want to talk now about our work is, okay, we have some quantitative version of the result of Milbus and Wolf under a bit more generalized spectral condition. Then also we are interested, okay, what does the spectral condition actually mean and where is it satisfied? So we prove that it's like necessary insufficient for this operator product to converge an operator norm. And we'll talk about that. Then, okay, we can extend this result under the spectral condition to unbounded generators if M and L kind of behave nicely together. And then we were like, okay, the spectral condition is nice, but we were interested in applying it to different models from quantum optics, for example, and we were aware that the spectral condition will not be met there. So we generalized to like a convergence of the operator product in strong topology where the spectral condition is not met. And I will talk about like an example there, which might be interesting to you. And okay, as the very end of the talk, I will kind of show how the result of the fourth point here can be applied to derive a result, not about the Zeno product, but more about like a so-called strong damping effect. But I will introduce this later. So, okay, now no quantum. I mean, it's quantum, but it's like general Banach space theory. So kind of we can forget about many of the technical stuff. We just have like some Banach space. We have some contraction M. So quantum operation is always a contraction. So like that's the only thing I really need. And I have a strongly, I have some contraction semigroup, and I will talk about it, whether it's like strongly continuous or non-continuous, depends a bit on the slide I show you in a minute. Okay, first I want to like motivate the spectral condition. And I'm interested in, okay, when does this operator, I want to find like some condition where on M, where it's clear that this operator product can converge. And okay, for all bounded L, and okay, if it's converged for all bounded L, then it needs to converge for the trivial case L to 0. Okay, when does this operator like M power converge as n goes to infinity is the question. Okay, and under which topology, right? So okay, clearly, if it converges in some topology to some operator, so some bounded operator, then this operator will be the projector on invariant. So it will be projector and it will be projector on invariant subspace of M. Like very easy to see. Yeah. Okay, now I motivate the spectral condition as first as something which clearly is sufficient to prove operator convergence of this operator norm convergence of this power of M. And then I will also show you a result which says that it's necessary. Okay, that's the definition of the spectrum, as we all know. And the spectral condition has 2 points, or 2 assumptions. One is the spectral gap assumption. So, okay, my contraction, as it's a contraction, it has like spectrum localized in a unit circle. But the spectral gap says, okay, there's like only one point on the spectrum on the peripheral part of the spectrum. So like only 1 point on the unit circle. And everything else is kind of like strictly in between the unit circle. So there exists some delta such that the rest of the spectrum is localized in a smaller ball, right? Okay, why is that nice? Because now I can do some functional calculus, or I can define some spectral projectors by looking at like curves which just like closed curves which only enclose one and the rest of the spectrum. So gamma is this curve which surrounds one, like big gamma, very bad notation to give a talk, I realized. And small gamma is the curve which surrounds like the spectrum with eigenvalue or spectral points strictly smaller than 1. And I can define by holomorphic functional calculus these operators first, where okay, P is where only surround at 1, and 1 minus P is the orthogonal complement. Well, not orthogonal, like it's the complement projector. Okay, this I can trivially write down. And then because M commutes with P, if I look at powers of M, then I have like these 2 guys popping up, and I can deal with them individually. One of them is very simple, because again, by holomorphic functional calculus, M times 1 minus P to the power N is just given by like this nice looking integral. But now I only integrate over Z, which have like which have modulus delta tilde. So this whole operator product converges exponentially fast as n goes to 0, right? So therefore, the only interesting part in the dynamics as n goes to infinity of that thing is like the part of M which belongs to the spectrum close to the spectral point 1. So okay, we can write this. We can just write MP as P. That's kind of the thing we expect to have in the end if Mn converges, M to the power n converges. And then n is just the difference. Here we can write down the difference again by holomorphic functional calculus. This is like some nice integral. And from that integral, it's very easy to see that this operator is quasi-nilpotent. So it has only a spectrum equal to 0. And maybe okay, already from like this formula on the top, I should maybe like motivate this P and N from things you might be more familiar with. So if this whole thing, like the whole setup would be finite dimensional, then P would just be the projector on the corresponding Jordan block with eigenvalue 1. And N would be the nilpotent operator, so the like the off-diagonal ones which pop around there. Okay, and now I'm just like hunting for some assumptions such that this M to the N converges. So I can just say, okay, why not just pick N equal to 0? Then surely, by what I've said before, M to the power N converges to P. Okay, so this is a sufficient condition for convergence and operator. And this is exactly what I take as my spectral condition. I have a spectral gap, and I have the quasi-nilpotent operator at the spectral point 1 being 0. So I have some kind of diagonalizability.
Doesn't that follow from norm M being 1?
No, that's the thing. I will talk about it. This is like a funny infinite dimensional logic. In finite dimensions, yes. Okay. There's an example which excludes this actually. Okay. Yeah, we were kind of talked about that as well, and it took us a bit of time to like realize that and then play around with that. And yeah. Okay, first spectral condition. I have some example just to motivate this, because you could be like, okay, in infinite dimensions, is there like any channel which actually satisfies the spectral condition? And at least we have like this nice Hoi channel we always like to play with. So it's the generalized depolarizing channel with sigma being some other state. So with 1 minus P, I don't do anything, it's just identity channel. With probability P, I replace with the state sigma. And then, okay, very easy to see the spectrum is just 1 minus P and 1. And the projector on invariant subspace is this replacer channel. So this is, I mean, it does not look like a projector. I mean, it's not a projector doesn't come from a projector on the Hilbert space, but it's projector on the trace class operators, right? And that's the relevant Banner space we consider here. And that thing, that thing is a projector, and the channel satisfies the spectral condition because you can easily calculate also the quasi-nipotent operator and see that it's 0. So now that's the argument Reinhard was pointing out in finite dimensions. I mean, you can ask, okay, is this n, is it maybe trivially 0 all the time? And that's the thing in finite dimensions, just by assuming that m is a contraction. That's the argument. So in finite dimensions, n must be nilpotent, not just quasi-nilpotent. So at some point, powers of n just disappear. Okay, this gives that n is equal to 0. Why? Because m is a contraction, therefore Pn is also a contraction. Okay, Pm we can write down by binomial formula, including n still. So we collect like all these powers in n. But now this sum gets truncated as this particular m, where n just disappears, or powers of n just disappear. And therefore, if n would not be 0, we get like a blow up here, because these how do you say, n over k just blow up. In infinite dimensions, this argument does not like immediately follow through, because you might not get like this truncation, right? So like this trick is not clear. Okay, but then you can still say maybe the quasi-nipotent operator might still be 0 by a different argument, right? But it's not the case. So we found like this counter example. It's not a quantum channel, but it's like connected to the Volterra operator on L2 on the interval. So there's this contraction which has a spectral gap, but a non-vanishing quasi-nipotent part. Won't write this down now explicitly, but if people are interested, I can talk you through this like after the talk or so.
But for channels, it's still an open question, huh?
Yeah, there we go. So this is like some, I mean, it's not abstract, but it's like some kind of not really to quantum theory connected contraction operator on some Hilbert space, where we can show that this quasi-nipotent operator is non-equal to 0, but we won't be able to find a quantum operation or channel which has a spectral gap but non-trivial quasi-nipotent operator. So if people are interested to construct this would be cool to see. I was not able to. Okay, now I want to kind of motivate the spectral condition a bit more, to show that it's also necessary for uniform convergence, right? So it's not just like some very technical condition, but it's kind of like fully characterizes operator norm convergence of the Zeno product or of powers of m. That's captures in our proposition. So we have 3 equivalent statements. Mn converges an operator norm, or it converges even with exponential speed, right? So it's first say why does it like always then also converge with exponential speed? But the point is because the first point is also equivalent to the spectral condition being satisfied, and we kind of seen earlier in the derivation I've did where I motivate the spectral condition that we actually get like this exponential convergence. So those 3 points are all equivalent, and they fully characterize convergence operator norm. Of course, it might still be very hard to check whether a given contraction satisfies the spectral condition. Right? So like that's the hard part, but it's still like a full spectral characterization of operator norm convergence. And that can be lifted relatively easily to prove convergence of the Zeno product in operator norm for bounded generators. And that's the result, and that's this quantitative version I was talking about. So I have a bounded generator. I have some contraction which satisfies the spectral condition, and then k in the limit of n goes to infinity, the Zeno product converges to an effective Zeno dynamics, where essentially the speed of convergence we got is like this 1 over square root n. I was talking about like this generalized spectral condition. This essentially is that you have like finitely many isolated spectral points on the unit circle that you can also do. Then you see some isolations. The dynamics looks a bit more nasty. That's why I didn't put it on the slide, but like it's the same techniques apply and you get it. So like if you have certain unitaries where the spectrum is nicely isolated, you get it as well. I just as a proof method, I don't really want to go through this, but I want to kind of mention what the techniques are. So we again use the holomorphic functional calculus we're now concerned not just with M, but with like this operator product here. And we cut out all the spectrum which belongs like strictly within the unit circle. And then with the remaining part, which has spectrum close to 1, we can use Chernoff square root n lemma. And that's exactly why we get like the scaling of the speed of convergence. And okay, now there is actually like a improvement of that result by Möbius and Rousset, by Cambus, and they proved tight convergence. So people expected from the like finite dimensional setup that under the spectral condition, at least we should like get convergence 1 over n, and this was shown by basically improving the Chernoff lemma. So that's what they did. Okay, what we then can also do is lift to unbounded generators. So we have an unbounded generator with some dense domain of some strongly continuous contraction semigroup. M satisfies still the spectral condition, and we need M and L to talk about, because already when L is unbounded on some general Banner space, like kind of making sense of PLP or some variant of that might be a headache, right? So we have this possibly very, very strong assumption, or I mean, it's a very strong assumption that ML and LM are both densely defined and bounded. And under this condition, we also get convergence in the of the Zeno product, but in the strong sense. And the way this is proven is we use our first, okay, we use a bounded approximation of our generator. So we take the Uceda approximation, which looks like that. Okay, those are nice bounded generators. Their operator norm blows up as the approximation parameter k goes to infinity. But strongly within the domain, they approximate the original generator. And then, okay, we lift our quantitative result for bounded generators and a coupled limit between k and n to get this theorem you see on this slide. Okay, and now do something completely different. So everything up until now was under the spectral condition, and you can say, okay, this might be very, very strong. And what examples do you have? The depolarizing channel, okay, more realistic physical things, maybe like, yeah, does the spectral condition there also hold? And then you can look at the beam splitter, the bosonic like attenuator channel, and you realize no. The spectral condition does not hold if you take M to be this attenuator channel. So how is it defined? You have this lambda strictly smaller than 1. And on coherent states, its action is very simply defined as just like kind of getting a new coherent state out, but with damped parameter alpha. And from that, it's kind of easy to see that it satisfies some strong power convergence. You take M now as being the attenuated channel, converges to this replacer channel, where you essentially replace every state with the vacuum state, so 0 photons. But in operator norm, you need to do this like uniformly. You have the supremum over all x. Okay, we can now lower bound this by the supremum over all coherent states. For every coherent state fixed, obviously because lambda is strictly smaller than 1, this converges nicely. But if we take the supremum before taking the limit, this is just constant 2, right? So we don't get convergence in operator norm. And therefore, because convergence operator norm is equivalent by our proposition to uniform convergence is equivalent to the spectral condition, we see that M does not satisfy the spectral condition. So all the results we had before, if you want to plug in M being this attenuator channel, you won't be able to like this doesn't give you any nice Zeno dynamics. Okay, but there is this theorem we came up with which saves us. Good. So this is for bounded generators L and M being a contraction which only satisfies now strong operator power convergence, right? So exactly like the attenuator channel would fall into this class of contractions. To some P, okay, P will again be the projector on invariant subspace of this M. Then what we find is strong convergence of the Zeno product to again the effective dynamics as we were hoping for. And I want you to talk you through a bit the proof technique, because it's very different, and because also the proof technique here I will then use for the strong damping, which I will talk about a bit later. So what do? We kind of consider now this discrete derivative, ln, which is defined there. Okay, as n goes to infinity, this is really just a derivative, so we get the generator out. But we get like a nice expression of the semigroup itself, right? We get like something which looks like 1 + 1 over n. Okay. And now we can plug this in and calculate a bit in our Zeno product. So we have like these two terms, and we have like this non-commutative power. And if we write this out, we see something which really looks horrible. So we would actually like to go back to the original thing, right? But if you stare at this sum a bit, so okay, what happens is you like multiply out and you collect all different powers of ln over n, and you sum like all these different powers. So like the first thing is just you don't see any ln over n, and then you sum over all possible k, and you need to have like all these combinations where ln can appear. And the way we can parameterize this is by summing like over this discrete simplex. So this is just what you see. And kind of what we like, the technique is then that we can control these sums. So we have this lemma which tells you if I have a sequence ln which converges an operator norm to some L or TL in this case, and some contraction which converges strongly, then these sums converge strongly again to kind of like the case part of the exponential series. So that's some technical lemma. I won't show you how to prove this, but that comes in handy because if you now again look at the Zeno product, exactly the sum appears, right? And now we can actually handle it. So as n goes to infinity, what we see, we exactly discover the exponential series back, and that's how we prove that we get effective Zeno dynamics. Okay, so this is, apart from not showing how you prove this lemma, this is the proof of this theorem for M only satisfying strong operator convergence. And then as the last thing, I do something not Zeno, but kind of related to Zeno, maybe a bit more related to the previous talks, where my dynamics is now governed by some, like we have two competing dynamics, some K and some L. And K is kind of the more dominant one. It gets kind of like amplified by this parameter gamma. So K can in our case be in possibly like it's an unbounded generator of some strongly continuous contraction semigroup on this Banach space. L is just bounded. So okay, first of all, we know by like elementary semigroup theory that like the sum L total generates a strongly continuous semigroup as well. Won't be a contraction semigroup anymore, but it's like still we get a nice norm bound which looks like that. And we are interested in the strong interaction limit. So we want that K is dominant. It's kind of plays the role of the M, where also M gets like n applications, but L it gets only finite time T. And yeah, we're interested in what happens if we crank up the strength of K. And that's the result. So we again consider the scenario where like K is strongly mixing. So as gamma goes to infinity, everything gets damped down into the projector on the invariant subspace. And then the result is that strongly again for all bounded generators L, also this effective sum dynamics strongly converges to an effective Zeno dynamics on the subspace P. And it's kind of proven exactly the same way as before, but the only thing you need to talk about is how do you actually get like an operator product out of this e to the gamma K plus L. And here we again consider like this difference Ln, which now looks slightly different. So we can write it down as this difference. So this calculation first only holds applied on some x in the domain of K, but then like we get some bounded operator out, so we can kind of extend to some bounded operator on the whole Banach space. And what we see is we kind of like this difference is basically our L, but we have this conjugation with these two semigroups and we need to integrate over S. And the operator is like order 1 over n, right? That's the important part. So therefore, as n goes to infinity, this difference just converges to 0 because like everything in the integral is bounded. And moreover, this also gives that if I consider my Ln, where I get rid of the n, this just converges to something which looks even closer to L, but still I have like this conjugation and the integral. So again, I can write my my dynamics like that. And I can take as m my e to the take tk, and therefore I can like, so I was not saying this, but here in this proof I only consider gamma to be a natural number. I can do this proof, and then I can show that kind of like this whole proof works also when I have like an nr that takes over like r some real number, and it goes like uniformly over r over a compact interval, and then it holds for all gammas. But now for you, gamma is just n. I can therefore write this the dynamics I'm interested in as an operator product. I can again write this operator in which I take exponents of as a sum. I again discover this quite nasty looking sum with all the difference L popping it up in different place. But now our lemma can treat this this sum, and I get something which almost looks like an which basically is an exponential series, right? But now not exactly with L. But the nice thing is that P is the projector on invariant subspace of that semigroup. So therefore, P kind of kills those, and therefore also the integral. And I get just the effective Zeno dynamics back. Yes, and that's kind of concludes my talk already. And I want to note a few open questions. Can we find, like that's the thing Daniel also mentioned, can we find quantum operation channels which have a spectral gap but non-trivial quasi-nipotent operator? That's open. We still have like only abstract contraction which satisfies this, but not something really related to quantum theory. Can we extend the results for unbounded generators? And then hopefully with like not some uniform boundedness assumption, but some pointwise boundedness assumption. And especially can we do it with, or hopefully also without the spectral condition, because like we assume the more physically relevant models lie within the set of like where we don't have a spectral condition. Like we had several examples of like from quantum optics where we can show strong power convergence, but uniform power convergence we don't believe to be true there. And then okay, the spectral like the result we have without the spectral condition that's completely non-quantitative. So we would like to have, or also the strong damping is non-quantitative, so we would love to have something quantitative there. Unfortunately, our proof does not really give that. But that would be really great, because I mean, one thing where like this, for example, the strong damping appears physically, Daniel was mentioning this to me once, is there are like certain proposals of dynamically error-corrected quantum computers where essentially you do error correction by having like some dynamics and you push down to the code space. So that would be like our e to the tk. And there are like certain proposals, but like doing this stuff rigorously and especially with convergence rates, this would be like really cool to do. Maybe that's a like first step in that direction. Yeah. And then I thank you for your attention.